Open polling this time while you guys see the numbers. So, welcome to Monday, as you're hooking up. So, we've done chapter 19, and we'll finish chapter 20 today, hopefully if all goes well. Then, we've introduced waves and sound. In other words, focused on the sound waves. So the rest of this week and next week will be on light. And treat them as waves. So they'll have many of the similar properties. And so most of what we introduce with light, you've already learned. Because it's waves. We'll just see how it applies to light and a few other things about it. And I won't lie. My favorite subject in physics is about light, so if I get a little giddy, forgive me now. I just think it's fun stuff. All right, how are we doing on this one? Got about half of you. So this one, wave interference occurs for what? Specific types of waves, or all of them, or? I hope those of you that are using responseware on a mobile device that will not let you use an app. So in other words, you have to go to a browser. If you're having trouble, I hope you've put in tickets, because they need to know about it. I've called them and put in tickets, but the more they hear them, maybe the more they'll address this problem. Curious, has anybody this semester had recurring problems with responseware where you had an actual app? You don't have an app, Candelaria. So it just seems to be those that don't have an app with the Windows-based phones. Okay, just checking though. Last time I talked to them, they're very friendly and willing to help, but they obviously haven't made it foolproof yet. Well, we'll move on with the first one and see. Let me know if yours didn't work. I can still give you credit. 10, 9, 8, 7, 6, 5, 4, 3. How you doing, Eddie? Yeah, tell me when you get it and I'll close. You're all right. There it is. Is that you? All right. Overwhelming all of these. You're right. As I've told you, this interference applies to any type of wave. Sound, water, light. Like I just said, all the stuff we're applying with waves now is going to apply to light. They act as waves. So yeah, it works for everything. This interference, constructive and destructive, where they can add together or subtract. All right. How about this? A standing wave is produced by reflected waves undergoing what? Remember the standing waves are when you got that incident wave, it reflects and comes back on itself? We did it with the wave machine over here with the bars, and we did it with the wave spring. It's called a standing wave because it looks like the wave's not traveling. It looks like it's staying put. What's going on there? Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Uh-oh. Okay. I'm just trying to decide whether to let you guys discuss it or just discuss it myself. You have a preference? You want to discuss it? You ask me? All right. It looked like mostly between interference and changes in amplitude. All right. So you got an incident wave coming one way. Say the crest might be up here, trough down, and they're traveling. They reflect and come back. So when they cross, we have a superposition. When they're in the same position, something can happen. They can constructively interfere or destructively interfere. So it's interference that creates a standing wave. That's when they constructively interfere. Yes, the amplitude is changing, but that's a result of the interference. That's why I like these questions, because sometimes it gets confusing between superposition, interference, constructive or destructive, let alone amplitude, frequency, period. With a lot of new terms maybe for some of you. So superposition is just when waves are on top of each other in the same location. Again, matter can't be in the same location. They don't like sharing exactly in the same location. But waves can. They can superimpose. When they do that, like in this case, they can interfere constructively or destructively. That changes the amplitude. For standing waves, we're not destroying it, so it's constructive interference. Questions? Concerns? Thoughts? Jokes? Amusing anecdotes? Okay. All right. Oh, I hit escape while I last hit turning point instead of PowerPoint, so it escaped out of turning point instead of PowerPoint. Bueno. Some of you are going to kill me because now we get to go back in. And I'm very sorry for that. I'll wait if that messes people up. All right, shock wave. What's that the result of then? Shock wave. Having to do with those sonic booms? Help you out if you can't remember. Shock wave was like the three-dimensional cone version of a bow wave, which was two-dimensional. We drew some pictures of like a plane moving forward and the sound it gives off, its speed relative to the sound wave's speed, and whether you go below the speed of light, the speed of sound, at the speed of sound, or faster than the speed of sound. I'll even help you. A shock wave is when you exceed the speed of sound. So the airplane's flying faster than the waves are traveling that it's emitting. And it causes this shock wave, which is the result of... Let's find out in 10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. 60, superposition. Very good. Very good. They're just all on top of each other. They make a wave front. They all just kind of bunch up, and that's that. All of them hit your ear at once when it passes by you. Boom! You hear that sonic boom, and it passes you. Good. They're just superimposing. Yes, they all are probably in phase, and they increase the amplitude, and that's why it's loud. As a result of superposition. Yes, Stephen? It does take more energy to break the sound barrier, yeah. Yes. Technically, it takes a little energy to get past that speed because it's that pressure wave that it creates. It's kind of like retarding its motion, so it takes energy to get past it. Once it's clear of it, yeah, you got that shock wave behind you, and so there's less energy now than getting through it. Just aside from the extra energy to just be going faster. But if you to get up to that speed, yes, you're crossing that barrier. It does take more. Yeah, it's because I was still babbling. So even though most of you are thinking about it, see, you'll just answer this question faster. All right, open polling. All right, in which of these examples of materials does sound travel fastest? Air, water, steel, or it's all the same at the same temperature? So sound does have a certain speed. Does it? Almost 30. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. You guys are split. You think it's air or steel mostly? Okay. It's the interactions. Remember my dominoes? The dominoes that were closer together, there were more interactions between them. And then the dominoes that were spaced further apart, there were less interactions. Which one did the wave travel through more quickly? The tighter one, the ones that were closer, where there were more interactions. So the speed of sound is generally faster in materials where they're closer together, but it's more about the interactions, as Eiffels come to. So in a solid, such as steel, sound travels a lot faster than it does in a gas, where they're generally farther apart. And so they can bump into their neighbors a lot more quickly in steel because they're closer together. So there'll be more interactions in less time. So it travels faster in steel. What would it next travel faster in, air or water? Water, because it's a liquid. So in general, sound travels slowest in gases, a little faster in liquids, and even faster in solids for that interaction. And for all of those, the temperature will affect it also. When things get hotter, they jostle around faster and they can interact with their neighbors more quickly. And so in general, when things get hotter, the sound will travel faster also for any of the materials. Will it travel further through air than it will through steel? What do you think? If you'd lose it through the interactions. That's logical. I'm thinking. I'm going back to my railroad track example where maybe you can't hear the train coming. That's the sound traveling through the air. But if you put your ear down to the rail, you can hear it coming before you can hear it coming through the air. So the energy is, yeah, that would work on tracks too. You'll just get a ticket. Oh, you can hear it through the material, the lines, because that's a solid material. Good example. So in general, we can say the sound energy is dissipated more in a gas than it is in a solid. Okay. Make sure I'm on. All right. The speed of sound varies with which of these? I hope you know it's at least C. But do you think it's also amplitude and frequency? So in other words, what's going to affect the speed of sound? Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. I know there's one more of you out there. Come on. And, all right, D. Correct answer is temperature. For me, amplitude's the clincher for me. Just because you make something louder or brighter, make those bumps bigger, doesn't change how fast it's traveling as a wave. In other words, I can talk monotone at one frequency. I'm talking right now. It's traveling to you at a certain speed, the speed of sound through air. I can talk even louder at the same frequency. It makes the amplitude bigger, but it's still traveling the same speed to get to you. So amplitude doesn't change the wave speed. Frequency. Think of it this way. If you listen to an orchestra down here, a bunch of different frequencies emitted. If they traveled at different speeds to your ear, the orchestra wouldn't be very exciting because you'd hear them at different times and it'd sound terrible. So you can send different frequencies out from your radio and they still travel at the same speed. They're just vibrating at different rates. That's like a wave that looks like this, a high frequency with short wavelengths, or one with low frequency and long wavelengths. They still travel at the same wave speed. You can change those, yes, but the speed of the sound doesn't vary with the wave speed. Does that make sense? And I believe I chose one more. All right. After that explanation, we'll see if you get this one right. So again, we four terms. Which of these is most closely related to the loudness of a sound? How loud it is. The equivalent would be with light, how bright it is. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Yes, amplitude. That's how loud it is. You're starting to get the differentiation between all these fun new terms? All right, you can put your clickers away. Thank you. Yeah. Between air, water, and still, what does sound travel the slowest through? What's the slowest thing it goes through? Oh, I don't know that off the top of my head. But gases, it travels more slowly in gases than liquids and solids. So we can narrow it down to that. So air, it goes relatively slower. But we could change the type of gas. I'm sure there's a gas out there that travels even more slowly through. I would think a heavier gas that doesn't respond as quickly. For example, air and helium. Helium's lighter and can move around more easily. Which one do you think it'll travel through more quickly? Helium, because the interactions can happen faster. So if we got a heavier gas, like sodium hexafluoride, some of you might have seen YouTube videos where people inhale helium and they talk higher, like Mickey Mouse. There's this sodium hexafluoride you can inhale and you talk demonically low. And so I'm pretty sure sound travels more slowly through that gas even than air. Doesn't fit. It's the interactions. In a solid, they're more closely together, so they interact with each other more quickly. So the wave can get through them faster, like the dominoes that were close together in solids. Liquids are less like that, so it goes a little more slowly through it. And gas even worse. But with gases, like the helium and the air, helium, they're going to have more interactions because it's lighter. They're easier to bump into their neighbors. They'll transfer that energy more quickly because they're moving around. Where the sodium hexafluoride, there's less interaction. There would be no sound whatsoever in a perfect vacuum because there's nothing to transmit that vibration, that wave. So yeah, Star Trek, when you hear explosions, wouldn't happen. But who wants to watch a entire space movie with no sound, right? So yeah, if you were out there, you wouldn't hear it because it had nothing to transmit through to your ear. So if a tree fell in a forest in the middle of space and there was no one around to hear it, would there be a sound? No, because there was nothing for it to vibrate to get to us. Yeah, Eddie? Yes, for a given material at a given temperature, its speed is constant. The speed of light is also constant, we're going to get to. It's always constant. Yeah, and I'm going to get to that, but your short answer is, yeah, a lot of people think, oh, well, the speed of light in a vacuum is faster than the speed of light in water. And we say that. Technically, though, the speed of light is an absolute. We learned that for every reference frame, and it is. It never changes. But it gets delayed going through water. It gets absorbed by a particle and then re-emitted. When it transfers from one particle to another, it's still going the same speed, but then it's absorbed and re-emitted. Absorbed and re-emitted, and that slows down the time it takes to get through it. Thus, on average, the speed through the water is more slow. But the light itself, it doesn't change speed. It's a little misnomer there. Yeah. Again, it's interactions. For sound, it's the interactions it needs to be transmitted. Light doesn't need the medium. It'll travel between empty space from particle to particle, and it goes at the same speed. But the more particles it runs into, the more interactions it has, it's the opposite effect. It slows it down, the overall time it takes to get through. See, for sound, it goes faster with more interactions, because that's what transmits it. For light, it slows it down. And that's something I was going to tell you, so now you know now. All right, now both these waves can do some things. The rest of chapter 20 here. Reflections. So if you have a surface, and we draw a line that's perpendicular to it. Remember our normal force? I know this is in the way for some of you and not others. Well, it'll move at some point. If you have an incident wave, the one that's coming in, and it's coming in this direction, then waves can reflect. You know this, light waves bounce off a mirror. It reflects. And so you get a reflected wave out. Waves, just so people are consistent, we use the angles with respect to that normal. In other words, the angle this incident wave comes in at, yeah, I know, sorry. Except I can't reach. The wave, we could have it with respect to here or respect to here. And to be consistent, so we all are talking about the same thing, we use the angle with respect to the normal. So if we say this is theta 1, the incident angle, then the reflected angle is also with respect to that normal, theta 2. And theta 1 equals theta 2 for waves. The sound wave came in, I talk here, hello! It bounces off of here and comes out at the same angle it went in at. Light will do the same thing on a mirror. A basketball will do the same thing when you bounce it off the floor without spin. Same with a billiard ball without English. So that's the law of reflections. It's that simple, but waves bounce around all the time. That's how you get echoes. When I talk, a wave comes straight at you, but a wave goes over here and reverberates. And so, acoustical engineers will design halls so that they reverberate the right amount. If it's too echoey, then you're just hearing the sound over and over and it's annoying. But if it's too dead, if you've ever been in a dead room, they sound really weird because none of it bounces off. And, you're listening to a symphony. You want to hear it resonate for a while. But not too long, because then it'll mess up the things that are playing afterwards, and you're hearing it all at once. So acoustical engineers will use these laws to either absorb the sound energy, different materials, like the tile absorbs the energy more than the hard surface where it reflects. And so they balance that game to control reflections and echoes and reverberations. There's another thing waves do, and it's refraction. I'm putting this in quotes. Bending of waves. It's what people usually say. And it's fine to think of it that way, but you should know technically it's not right. Bending of waves. Reflection occurs where it stays in the same medium. It starts in air, it hits a wall and bounces off back into air. Refraction changes mediums. So an example is water. This air, this water. Again, you draw a normal, perpendicular. You have an incident wave come in. Water is not very reflective. It depends on the smoothness of the surface, but it can reflect some of the light. So reflection does happen. There's a little light that reflects. So you get a reflected wave. But most of it will go into the water because water is transparent. When it does that, it appears to bend. You ever seen, you stick your straw in your cup of water and it looks bent? Well, that's because it travels more slowly, it's delayed more, in this material. And so instead of going straight, as if it were undisturbed, it slows down a little, in this case. You still have your normal down here, it's perpendicular, and it actually gets bent this way. It's better to think of it as being redirected. Redirected. The wave doesn't like go, whew! It's just every time it goes into a new material, it can change directions. And so this would be your incident angle. Here's your reflected angle. Those would be the same. Theta 1 and theta 2. But you also have this refracted angle. Theta 3 there. And that's going to be different than the incident angle. And there's a law called Snell's law that tells that difference, that relationship. Oh, I won't tell you about it for now. Well, you just want to know it changes. I want to try to explain why it does that. This is smooth cardboard, poster board, and this is some cork. It's two different materials. Here's a wave. It's like a wave front that's coming at you, like we've seen with the sound waves. This wave front that's coming out. And here's a section of it. If I put it down on here, and it starts heading off in this direction, right? Watch what happens when it changes mediums. We'll see if it works today. I don't know if you could tell. Go a little slower. Let's try it even a shallower angle. Maybe it'll be more conspicuous. You see it ended up going that way? Let's do it again. Yeah. Do you see that it bends or it changes direction? If we put these together, those angles, that's what happens. Why? Well, let's look at this wavefront. When it comes, whoops, when it gets here, this edge of the wave is traveling in the new material. This edge is traveling in the original material. It travels at different speeds in the two materials because, well, we've discussed that plenty today. If this one it's going faster in, and this one it's going slower in, this one gets further along, and it turns. It's like driving your Jeep where one wheel's in mud and the other's on the road. One can go faster while the other's spinning out, and you turn. That's what happens with these waves, any wave, sound or light. And so refraction happens because the speed that they travel through those different materials changes. And so the wave changes direction. If it came out of the water, say this was your incident wave. When it switches into the air, it'll bend again. So it works going the other way as also. If I try to come out of the cork, watch it. Whoops. A little steeper. Yep. You see it bend? Change direction. Because once it gets into here, it travels faster and gets ahead of this part of the wavefront. That's refraction. It happens for sound waves and light waves. And it'll bend in the direction towards back to whichever medium it travels more slowly in. So sound, when it travels different in cold air versus warm air, it'll bend one direction. Light will do a similar thing, whichever one it travels more quickly in versus more slowly in. Questions about that? Yeah.
So where is it active? Is it really
Exactly. Yeah, let's say there was an object right here, a coin, right? You want that coin. If your eyeball was right here, the light from this coin would come up, it would refract and change directions at the interface, head that way into your eye. You see it as if it came from this direction. So you will think the coin is over here. So when you reach to grab it, you'll miss. If you reach where you think the light came from, but it got bent here, then you'd be a little wrong. So when you get to those questions in homework, I think there's one about shooting something with a laser in water, like a fish, versus a spear. Because where the light travels isn't exactly where you think it came from because of that bending. This example, the way I drew this, that's the way it'd be for light. So it goes faster in air than it does in water because there's more interactions here, since we already discussed it. So it's going to take longer to get through the water for light because it's impeding its motion. And so this wavefront goes faster and it bends towards the normal as it goes into slower materials. It's opposite for sound because of the opposite effect. Your author does a good example I want to share with you. Where did I write that? See if I can get it right. Okay. Let's say you have two camps. You got some tents over here. I'm not an artist by now. And you got a lake. And so you're sitting over here in one camp, and you got other people over there in a different camp. And during the day, you don't hear them very well. You're like, "Hello over there, how you doing?" "I'm doing okay." And you have to shout pretty loud. "Did you have fun today?" "Sure." When you're a scout, you have deep conversations. But at nighttime, you're trying to go to sleep in your tent. I don't know if anybody's ever noticed this. And it's like they're just outside your tent. You can hear them as clear as day. Because they're probably in their tents just talking. Normal, not even shouting. So why can you hear them better at night than you can during the day? The temperature changes. Yeah. At night, let's see, the watt. I knew I should have drawn a picture because I always got to get this the right way. Well, what we do know, let's work backwards. This is how we work out problems when we know what's going on. All right, if you're talking, then the sound wave's kind of going like this. It makes it over to you, and you hear them well at night. Where in the day, it curves up and out. There's that bending. It's refracting. It's changing directions. What would cause it to refract in this direction? Let's see. We're going to either have warm air on top and cold air below, or vice versa. Which one does sound travel faster through? Warm air or cold air? That's what we got to remember. Which one will have more interactions? Warm. That's how I'm going to remember it. So it's going to travel faster through warm air. All right. If we have a wave front, here I got a ruler. Let's say this is our wave front coming out. If this side's traveling faster, it'll bend that way, won't it? So it's traveling faster up here. That's the warm air. And this is the cold air. And that must be the case over a lake at night. So that the sound waves that head out get bent right over to the other side. It'd be the opposite effect during the day, yes. Okay. Correct. It travels more slowly in cold air. For sound, it needs those interactions. Warm air is jostling around faster. That's the higher temperature, average translational kinetic energy. And so the wave is transmitted through warm air more quickly. So two different mediums as it's trying to change, and it changes directions. It refracts back down. Can you see a similarity with light? I'll probably bring it up again, but light will bend and kind of does this bending thing. What do we call those usually? You see where I'm headed? You can see an image where it isn't. A lot like this. That's it, a mirage. You're out in the desert and you got the hot air above the sand or above a road. You can have light refract. And it'll have this kind of curved nature to it as it's changing direction, as it goes from warmer to colder or colder to warmer, as it progressively gets different. And so, yeah, you can see headlights. It looks like there's water ahead in the hot road. You ever notice that driving along? So that's like you spotting over here. But the light was like coming from the headlights, went down into the hot air, got refracted, comes back up into your eyeball. So like headlights. If the light's off of this, heads off in all directions, that's why you can see it. But let's say some light goes down towards the road. But it's a lot hotter down there. So the light will get bent, come up to your eyeball, and you see it as if it came from down here on the road. If you ever notice that, you can see images of street signs or car headlights in that water that looks like it's on the road. There's not water there. That's just that refracted light bending up into your eye. Same occurs in the ocean. Some people will see a ship upside down above another ship because of this difference in temperature over water. Or in a desert is the most common. Again, because of the hot air nearer the sand. All that is refraction of waves. That's my point. Because waves travel at different speeds through different materials, they can change direction when they try to change mediums. It's a cool effect. You can do lots of fun things with it. Two minutes, yada yada. There's one more way to think of this. Might help you. With waves. It helped me, so I want to share it. Let's say you're on the beach. Here's the sand. Here's the water. And you got somebody that needs help here. They're drowning. Help, help. And you're over here on your lifeguard tower, right? All right. Basically, you need to get to them as quickly as possible. There's a principle that you can help explain this bending. And it's in getting from point A to point B, waves will follow the shortest path in time, not distance. What's the shortest path in time In other words, how can we get from A to B the most quickly? The obvious is, well, let's just go straight. Let's look at it. If you're running through the sand and then you're swimming through the water, which one do you move more quickly through? The sand. You can run faster on sand than you can swim through water. So you figure out how long that takes, but then you slow down and you got to travel all this distance and it'll take a while. So you could think, okay, let's minimize the distance in the water because that's where we go more slowly, right? So let's go, that's the shortest distance in the water, right? So now we can run really fast across the sand. We'll cover more sand. This is a lot longer distance, but we're in the water less. So that you might think could be faster. But it's somewhere in between. Because this is faster, yes, but you've had to increase the distance a lot here, and that'll slow you down compared to this. So it's actually somewhere in between. Let's head that way in the sand a little longer, and then swim out to them. So you're still spending less time in the water than here. So that'll go faster, but you're not traveling farther than you need in the sand. So that the big thick one there in the middle can help you represent refraction of waves. It's the shortest distance from A to B in time. Can you see it changing direction? It looks like our refracted ray over here. So that's what sound waves and light waves do when they change mediums. All right, it came up earlier, but this is where it shows up in chapter 20. Forced vibrations and resonance. All things want to naturally vibrate at a certain frequency, like that. It naturally wants to vibrate like that. So if you drive it at that frequency, let's see, this naturally wants to vibrate at that rate. Do, 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 do. You can figure out the period, right? How long it takes to go up and down once. You know the frequency. Even if it's a larger amplitude, it's the same frequency. It wants to go. So if I drive it at that rate, that's resonance. And the amplitude gets bigger. You put more and more energy in. Driving frequency matches natural frequency, resonance. Resonance are when those two match. If I go faster than that, still make it vibrate, but if I don't hit resonance, the amplitude doesn't get bigger. There's not more energy put in. And if I go too slowly, sure, I can bend it, but we're not hitting resonance. It wants to go at that rate. If I make it shorter, whoop, the wave's going to be shorter. It's like it's under greater tension. It's stiffer. Do you think it'll vibrate more quickly or more slowly? More quickly. The frequency increased. I essentially changed the medium. It has a new natural frequency. So I have to drive it faster. Now it works. So that's resonance. I'm sure you guys have blown in bottles before, right? So I'm changing the pressure up here. We know about that. And so that causes a slug of air to vibrate in and out in this reservoir. It's got a certain size. And so it oscillates, pushes the air out here, and we hear it. This, based on its size, it sets up a wavelength that determines the frequency. Frequency and wavelength go together. It naturally wants to vibrate at that frequency, so when I drive it, that's what comes out. What do you think will happen if I remove some of the water? It's a lower frequency, which corresponds with longer waves. We're not changing the wave speed. It's the speed of sound and air. It's still traveling to us the same. But look, we got a bigger wave. Takes more distance, so it's going to vibrate more slowly. You can do even more. And even lower. Those are some resonant frequencies. This has resonant frequencies. These are called boom whacker tubes. We're open here. The length will determine the standing wave, the incident wave and the reflected wave. The wavelength will help determine what pitch we hear. That's the pitch it likes. So if I drive it, it'll cause the air inside to vibrate at its natural frequency based on its size and shape. And we hear that. The sound travels to you. If you change the size and shape, smaller wave, what do you think will happen? Higher frequency. Again, same wave speed to you. All right, here's a classical piece. Mozart really wrote this. See if you can tell what it is. He really did write that when he was a child. You know, it's the tune too. It's different. The ABCs, Mary Had a Little Lamb, or Ba Ba Black Sheep. They're all the same tune. When he wrote it, he called it Vous dirais-je, Maman. He's French. Check this out. This is exactly half the length of this one. How do you think the frequencies will compare? Higher. Say again, higher, but what? Higher frequency, but same pitch. Remember, pitch is subjective. So you're correct. Both of these are C notes. But one is an octave higher than the other. The wave is exactly half the length. So it's vibrating exactly twice the frequency, in there, which is an octave for musicians. Now, I'm going to take this octavator cap and put it over the end. The sound can get out both sides. Now it can only get out one side. You think it'll be higher, lower, or the same? Now they're the same. This one travels this length. This one has to travel down and back out. So it's essentially the same wavelength now. A closed tube, some instruments are like that. An open tube, both on both, and some instruments are like this. So you can change the wavelength and thus the pitch you hear that way. Let's end with, I'll save that one. My favorite. Yeah, let's do this one. Whoopee cushions. And if you've never had the self-inflating ones, they're awesome because you don't have to blow them back up. So this puts out a bunch of different frequencies all at once. It's kind of like white noise. Shh. Very quickly, this is your vocal folds. Your vocal folds vibrate. You increase the pressure with your diaphragm. It forces air out between your vocal folds. They let the air out. It goes faster. There's a decrease in pressure, Bernoulli's principle, and they slam back shut. They're vibrating. That makes the sounds. But what we hear is your throat, your vocal tract, your throat space, your mouth space, your nasal space is a tube. It's this space. So if you change the size and shape of your vocal tract, you can change what frequencies your vocal folds are making. And that's why people sound different. Example, we hear this. Let's put it in somebody with a lot of space in their vocal tract. You hear that frequency. It's filtered out. Put it in this one. Let's make your vocal tract smaller. And so even though you can talk at the exact same frequency, A, E, I, O, U, same frequency, same note we'd say. But they sound different because you're filtering them. You're changing the shape of your vocal tract by moving your tongue up and down, back and forward. And you're changing the resonant frequencies that want to be set up. You're driving it with your vocal folds, but you're filtering it and resonating through your vocal tract. So there. We'll do some more Wednesday. Thanks.